Welcome to this lecture on the moments of the t-distribution. Today, we are going to explore how statisticians measure the shape, center, and spread of probability curves when working with small sample sizes. If you have ever wondered why small samples are so unpredictable or why extreme surprises happen more often than a normal bell curve would suggest, you are in the right place. We will build this understanding from the ground up. Let us begin by imagining you are trying to balance a perfectly symmetrical seesaw on a playground. The exact center where it balances perfectly is its mean, or first moment. Now, imagine how the weight is distributed. If people sit at the far ends, it is much harder to move. This spread of weight is the variance, or second moment. In statistics, moments are simply mathematical measurements that describe a probability curve. For the t-distribution, the shape depends entirely on a single parameter called degrees of freedom, represented by the Greek letter nu. A very strange and important rule here is that a moment only exists if the degrees of freedom is strictly greater than the moment number. If you do not have enough data points, the mathematical properties become completely undefined. Now that we understand what moments are, let us look at the first moment, which is the mean or expected value. The probability density function of the t-distribution is perfectly symmetric around 0, just like the standard normal distribution. Because the left side is a perfect mirror image of the right side, the exact balancing point of the curve is exactly at 0. However, this is only mathematically true if the integral of the curve actually settles down to a finite number. Therefore, the mean is 0, but only if the degrees of freedom is strictly greater than 1. If the degrees of freedom is exactly 1, the tails are so incredibly massive that the mean does not mathematically exist. This concept leads us directly to our first formula. The expected value of the t-distribution is written simply as E of t equals 0. Conceptually, this comes from the perfect symmetry of the curve we just discussed. In this equation, E of t stands for the expected value, which is the mathematical term for the mean or average. The value is exactly 0. This tells us that if we take many small samples and calculate their t-scores, the average of all those scores will center perfectly around 0. But remember, what changes physically if the degrees of freedom drops to 1 or below? The formula breaks down. The tails become so heavy that the balancing point cannot be calculated, which is a fascinating property of small samples. Now that we have established the center, let us understand the spread. The second central moment is the variance, which measures how widely the data is spread out around the mean. Because the t-distribution is used for small samples, there is inherently more uncertainty in our estimates. This uncertainty physically translates to a wider, more spread out curve than the standard normal distribution. While the standard normal distribution has a variance of exactly 1, the t-distribution will always have a variance strictly greater than 1. This reflects the extra uncertainty and the presence of fatter tails. As your sample size grows, this uncertainty shrinks and the spread of your data becomes tighter and more predictable. This brings us to the mathematical formula for the variance. The variance of the t-distribution is calculated as nu divided by the quantity nu minus 2. Conceptually, this formula captures how the spread of data behaves as sample size changes. Let us break down the symbols. Var of t represents the variance, which is a measure of spread. The Greek letter nu represents the degrees of freedom. This formula is only valid when nu is strictly greater than 2, because the second moment requires it. What happens physically when nu increases? As the sample size grows infinitely large, the denominator gets closer to the numerator, and the variance shrinks down, approaching exactly 1. This perfectly matches the standard normal distribution. Having covered the center and the spread, we now look at the third and fourth moments, which describe the lean and the pointiness of the curve. The third central moment measures skewness, which is how much the curve leans to the left or right. Because the t-distribution is perfectly symmetric, it does not lean at all, so its skewness is exactly 0 provided the degrees of freedom is greater than 3. The fourth central moment is used to calculate kurtosis, which measures how heavy or fat the tails of the distribution are compared to a normal distribution. We often look at excess kurtosis, which tells us exactly how much extra tail weight the curve has beyond a standard normal curve, indicating a higher chance of extreme surprises. To measure this tail weight precisely, we use the excess kurtosis formula. The formula is gamma 2 equals 6 divided by the quantity nu minus 4. Conceptually, this comes from the complex integration of the fourth moment. Here, gamma 2 represents the excess kurtosis and nu is the degrees of freedom. The number 6 is a mathematical constant derived from the integration. This formula is only valid when nu is strictly greater than 4. What changes physically as nu changes? Because nu minus 4 is in the denominator, a small degrees of freedom gives a massive excess kurtosis, meaning extreme outliers are very common. As nu approaches infinity, the denominator becomes infinitely large, so the excess kurtosis approaches 0, which is the exact signature of the standard normal distribution. Before we move on to calculations, let us see this with a concrete visual example. Here, we are looking at a graph comparing two probability curves. The horizontal axis represents our data values and the vertical axis represents the probability density. The solid blue curve is the standard normal distribution, which has a tall peak. The dashed red curve is the t-distribution with 3 degrees of freedom. Notice how the t-distribution has a lower peak at the center. More importantly, look at the arrows pointing to the far left and right. The tails of the t-distribution stay higher above the horizontal axis as you move away from 0. These fat tails are exactly what the excess kurtosis formula measures, proving visually that extreme values are much more likely in a t-distribution. Now that we have seen the formulas and the visual intuition, let us apply them to a real scenario. A quality control engineer takes a small sample of 6 batteries to test their lifespan. The degrees of freedom for this specific test is 5. We are asked to calculate the mean, variance, and excess kurtosis to understand the shape of this small sample's probability curve. We chose these moment formulas because they perfectly describe the distribution's behavior. First, we check the condition for the mean. Since 5 is strictly greater than 1, the mean is mathematically well-defined. Because the curve is perfectly symmetric, the expected value is exactly 0. This means the center of our probability curve is perfectly balanced at 0. Continuing with our battery example, we next calculate the variance to see how spread out the data is. We use the variance formula. But first, we must ensure that our degrees of freedom is strictly greater than 2. Since our value is 5, we can proceed safely. We substitute 5 into both the numerator and the denominator. Subtracting 2 from 5 in the denominator gives us 3. The resulting fraction is 5 divided by 3. This gives a variance of approximately 1.67. This value is significantly larger than the standard normal variance of 1. Physically, this higher variance mathematically proves the high uncertainty of using such a small sample of batteries. Finally, for this small sample, we calculate the excess kurtosis to measure the fatness of the tails. We take the excess kurtosis formula, which requires the degrees of freedom to be greater than 4. Since our value is 5, we are allowed to use this formula. We substitute 5 into the denominator and subtract 4, which leaves us with exactly 1. We are now left with the simple fraction of 6 divided by 1. This gives a final excess kurtosis of exactly 6. This is a very high number compared to a normal distribution, which has an excess kurtosis of 0. Physically, this means the engineer should expect extreme outliers, like a battery dying immediately or lasting forever, to occur much more frequently. Now that we have seen the extreme uncertainty of a small sample, let us see what happens when we increase the sample size. The engineer realizes that a sample of 6 batteries is too unpredictable. She now takes a much larger sample, giving a new degrees of freedom of 30. We want to know how much the probability curve has improved. We start by calculating the new variance. We substitute 30 into the numerator and the denominator. This is perfectly valid since 30 is much greater than 2. We subtract 2 from 30 to get 28. The fraction simplifies to 30 divided by 28, giving a variance of approximately 1.07. Notice how much closer this is to 1? The spread of the data is shrinking, meaning the estimates are becoming much more precise. Continuing with our larger sample, we now calculate the new excess kurtosis to see if the tails have thinned out. We substitute 30 into the denominator of the excess kurtosis formula. This is valid because 30 is strictly greater than 4. We subtract 4 from 30 to get 26 in the denominator. We divide 6 by 26 to find the final value. The new excess kurtosis is approximately 0.23. This is drastically smaller than the previous kurtosis of 6. Physically, this means the tails have thinned out significantly. The curve now looks very much like a standard normal distribution, meaning extreme surprises are much less likely to happen. Before we conclude, let us understand why these moments matter so much in real life, outside of engineering. When financial analysts model stock market returns, they often use the t-distribution instead of the normal distribution. Why? Because stock markets frequently experience extreme crashes or booms, which live in the fat tails of the probability curve. If an analyst assumes a normal distribution, which has a variance of 1 and an excess kurtosis of 0, they will severely underestimate the risk of a market crash. By using the t-distribution and calculating its exact variance and kurtosis based on the sample size, they can accurately predict how often these wild, extreme fluctuations will occur. This mathematical property literally prevents banks from going bankrupt during financial crises. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the moments of the t-distribution perfectly capture the uncertainty of small sample sizes. Second, while the mean is always 0 due to perfect symmetry, the variance and kurtosis are heavily dependent on the degrees of freedom. Finally, we saw a beautiful mathematical progression. As the sample size grows, the variance shrinks to 1 and the excess kurtosis vanishes to 0. This transforms the unpredictable t-distribution into the highly predictable standard normal curve. You now have a solid understanding of how to measure and interpret these distributions. Great job following along.